Okay, so we're going to work on problem one of the fourth self-assessment problem set here. And what we have is a set of data which shows that some substrate S, could be, I don't know, lactose being converted into glucose plus galactose or whatever, and the concentration is declining over time. And what we want to do is figure out, does this simple little model here agree with the data? And by checking that, we want to work out what the value of this constant k is. It's called technically a first order rate constant. This little model actually here describes radioactivity very well, and also kind of population decline and things like that. It's called an exponential decay. So the first thing we want to do is get our data here and copy it into Excel. Okay, so there's our data. So it's very stripped down, if no headings or anything like that, because when we're importing this into Berkeley Madonna, we don't want any kind of stuff lurking around. So we're going to save this file as a special type of file, not an Excel file. So I'll put it into, I don't know why it's asking me that. Let's say S data. Right. For question 4-1, and it's not an Excel workbook. I want to remember we want a comma delimited file, a CSV file. That's what Berkeley Madonna wants from us. So we'll do that. Okay, so now we want to code in this equation here into Berkeley Madonna. Now luckily the time span is 10, which is the default. So I don't have to change the stop time. I'm not going to fiddle with the DT. Now I've inserted a DT out of 0.25, and that'll reduce the size of the data file that my simulation churns out. It just makes things a little bit simpler later. Actually, I might make that 0.5 just so we're not churning out rows and rows of data. Okay, so the first thing is our differential equations. We've only got one of them, and I'm going to code in capitals as is my habit. So d dt of s is equal to minus k by s. We're going now to have initial conditions, or initial condition, and that'll be initial value of s equals s0. And then we're going to have parameter values. So as I said before, it's good just to get into a routine and do these things in a certain order. You don't have to use the order I do. And I'm sure I'm not entirely consistent, but it is good in general to be kind of systematic. Even when you're drawing graphs in Excel or whether you're writing Word documents, just adopt the same approach. Bit of a misspelling there. So the parameter values, S0 is just the initial value of S, which is 1. Now, the k is the thing we're really looking for here. So we're going to give it a value of 1, but we're going to recognize that that's just an estimate. This is just an initial guess for what k is. And what we're going to do is we're going to fit the model to the experimental data, and the algorithm within Berkeley Madonna will adjust k so that we get the best possible relationship between the model and the data. So I'll run that now. So there's simulation output. I always like to have my parameter window. Actually, I'm going to reset that. See, this is a funny thing about Berkeley Madonna. Sometimes you run a program and you're not too sure which value it's using. So it's good that this has happened now. Because I've been playing with this earlier, there was a k here in the memory that was not equal to 1, even though my code said it's 1. So it's really, I think there's a little bit of a bug in the software. You really always need to have your window open, because your parameter window, because the software takes the values from the parameter window. So I'm going to run that again. And there's what S is, okay? With a value of k is equal to 1. And there we go, in tabular form. So what I'm going to do now is, actually I leave it in tabular form, is I'm going to do the curve fit, and I'm going to import a data set and just find our file. What was the file? I think it was S data for question 4.1. That's where our data was. Okay, obviously I've been making sure this whole thing is working, so there are a few things lurking around from my earlier visits to this problem. So, okay, so we've chosen that K is to be our parameter. I didn't show you that there, so here you add your K. We're fitting the variable S, it's the only one in the problem, and we're using data from this file here. And I'm going to run it, and we can see now that it has changed K to essentially 0.1 there. So from an initial value of K is equal to 1, it's converged on a better value which fits the data better. So what have we over here? Well, what we have over here, the S1, that's the simulation output. And this funny thing here, and this is another quirk of Berkeley Madonna, this is actually the raw data, but Berkeley Madonna has filled in gaps in the raw data. It's kind of interpolated between the raw data. So I don't want that. So I'm going to click that off. All I want is the simulation output, which is here. So I'm going to click here, Control C, and now I'm going to go into Excel. So here's my experimental data, and now I'm going to add in my simulation results. Okay, so the first thing I'm going to do is draw my experimental data. And I'm going to, remember, simulate, actual experimental data is always just a scatter plot. So it's the raw data. I always like to click this off. That always annoys me. And now I'm going to add a second plot. Excuse me. See, I didn't want to make this file too gigantic. That's why I used a DT out of 0.5. And then this is going to be this. Okay, so now we've lots of dots here, and what we want to do is make this a little bit clearer. So I'm going to say change the series chart type. And the second series I'm going to make like that. So I remember I want the simulation to be a smooth curve, and I want the experimental data to be discrete points. So I get that there. And now I have a nice representation of the comparison between the simulation, which is the orange curve, and the experimental data, which are the blue points. So that should be the kind of norm as to how you present results when you're comparing data with simulations. Smooth curve for the simulation, discrete points for the experimental data. So the net result of that simulation is that the model appears to be a really good fit, and we got K really to be equal to 0.1. I think it's 0.0996 or something, but essentially K is equal to 0.1. So even though our initial guess was a bad one for K, we had guessed K to be equal to 1. The algorithm was able to cope with that, how poor that guess was, and converged nicely on the value of K is equal to 1, and gives an excellent fit between the data and the model.